Hello students, this is Dr. Faizan Mirza. We are discussing transport across the membrane, and we know diffusion is diffusion, active transport, and osmosis and endocytosis, exocytosis are the main processes of how movement occurs across and through the membrane. Diffusion. So you can recall diffusion. Diffusion is the movement of molecules down the concentration gradient using the kinetic energy of molecules, and the metabolic energy or the energy in ATP breakdown is not utilized in diffusion. There are factors that govern diffusion. So rate of diffusion is directly dependent on concentration gradient. The higher the gradient or the steeper the gradient or difference of concentration, the faster the diffusion will be. The rate of diffusion is also directly proportional to the surface area available. The larger the area available for diffusion to occur, it would occur even faster. And the rate of diffusion is directly proportional to temperature as well. So higher the temperature, you provide it with more kinetic energy. So the molecules start to move faster and the rate of diffusion is faster as well. The rate of diffusion is inversely proportional to the size of molecules. So the larger the molecule, the slower the diffusion will be, and the rate of diffusion is also inversely proportional to the distance across which the diffusion has to occur. So the shorter the distance, the faster the diffusion would be, and so on and so forth. We have to discuss Fick's first law of diffusion. The statement of the law goes as rate of diffusion across a surface is proportional to the area available and the difference of concentration of the diffusing substance. Mathematically, we can represent this Fick's first law of diffusion by the equation J is equals to minus dA dC upon dx, where J stands for the net rate of diffusion, A is the area available, dC over dx is the concentration gradient, and this capital D is the diffusion coefficient. The negative sign here is the direction of diffusion, which is obviously down the gradient. This capital D, the diffusion coefficient, is proportional to the speed of the diffusing substance, which means it will be faster for substances which are moving faster will have a higher diffusion coefficient, and substances which the diffusion coefficient will be small will be the smaller substances. It will be small for the larger substances, and as well as it will be small for the viscous medium. Diffusive permeability basically tells you which substances can cross the lipid bilayer. So lipid soluble substances which are non-polar in nature, they diffuse easily, and small uncharged water soluble substances can cross the membrane very easily, whereas any substance which is water soluble and its MR is greater than 200, it cannot move through the membrane by simple diffusion alone. It needs facilitation through a transport protein, which could either be a channel protein or a carrier protein, and that's called as the facilitated diffusion. Next, we have to study osmosis. So to study osmosis, let's recall that the ability of water molecules to move is called as water potential. It is denoted by the Greek letter psi. This Greek letter psi represents the water potential. Pure water is having a water potential of 0 kilopascals. Kilopascal is the term which the unit we are using for pressure here. So if you add solute to water, its water potential starts to get lowered. So it would get lowered to minus 50, for example, by adding some solute. You add even more solute, it becomes minus 100 kilopascal, keeps becoming more and more negative. So no solute added, it would be 0 kilopascal. With less solute added, it would be negative, and with more solute added, it would be even more negative. So dilute solution and concentrate solution, I guess you can very well picture which one will be more negative. We need to study a term osmole. The number of osmotically active particles are called as osmoles. Osmoles are 1 mole is equals to 1 osmole, which equals to 6.02 into 10 to the power 23 particles. So this is how we understand the term osmole. Let's take an example here. We have 3 solutions, and all the 3 solutions are 1 molar each. We have 1 molar glucose, 1 molar sodium chloride, and 1 molar calcium chloride solution. All of them have the same number of moles, A, B, and C. I have mentioned these solutions to be, but they don't have the same number of osmoles, because when you dissolve them in water, glucose will not ionize, but sodium chloride will ionize to form sodium and chloride ions. So this 1 molar sodium chloride will have 2 osmoles, 1 osmole of sodium and 1 osmole of chloride. Similarly, calcium chloride 1 molar solution will dissociate into 3 ions, 1 calcium and 2 chloride ions. So it will end up having 1 osmole of calcium ion, 1 osmole of chloride ion, and 1 osmole of chloride ion again. So let's suppose if we have 3 solutions A, B, and C, each of these are separated by a semi-permeable membrane in a beaker. Let's suppose I have this kind of a situation where I have these three solutions. This is 1 molar glucose, 1 molar sodium chloride, and 1 molar calcium chloride. Although all three of them have the same molarity, but we know that the solution C is having the highest osmolarity, B is having a lesser osmolarity, and A is having the least osmolarity. So according to the principle of osmosis, water will start to move in this direction, that water will move from A till B, and from A and B it will move to C down the water potential gradient, because C is the most concentrated solution of all. We will see that the volumes of these solutions will start to change, although initially all the three would have been the same. So A will lower up in volume, the volume of B will start to increase, and the volume of C will rise even further. The difference can be seen that A decrease, B increase, and C increase even further, and this is how osmosis occurs. So you can very well place this example inside a cell, and how the cell would end up expanding because of pulling more water molecules, or the cell will end up shrinking if a lot of water goes out. Either of the condition will cause the cells to burst, because animal cells are not protected by cell walls, so our cells are very vulnerable to any kind of osmotic changes. The term osmotic pressure is basically linked with how fluid exchange occurs, and I already discussed it there as well. Osmotic pressure is the ability of osmotically active solutes to attract water molecules towards itself. The number of osmotically active particles is proportional to the osmotic pressure. So if the increased rate of osmosis would mean that more water molecules will move into that solution, because there are more solute particles which are osmotically active, and they are pulling more water molecules towards themselves. We studied how at the end of capillary bed, which is near the venule, how there are a lot of osmotically active particles, the large proteins in the capillary, which pulls a lot of water molecules back in from the tissue fluid into the capillary. So that we studied this osmotic pressure principle there. The next law that we have to discuss here pertaining to osmosis is Van 't Hoff's law of osmosis. It is mathematically represented by the equation of pi is equals to RT phi IC. This is equation 1, and the equation 2 is osmolarity is equal to phi IC. This symbol here can be read as phi. This is Greek letter. So pi is the osmotic pressure, I is the number of osmotically active particles which are present in that region. And if we go, R is the ideal gas equation constant, and T is at absolute temperature. C is the molar concentration of the solution, and we know that the value of RT can be tabulated here, which will be 22.4 liter atmosphere per mole. Phi actually is the osmotic coefficient. Then this osmotic coefficient is less than 1 for physiologically important ions. Let's take an example here. These values are already provided in the literature. The solutes are mentioned in there when they are dissolved in water. You will have these number of I's, and this is the phi value given to you. For example, if you are given a question of calculating the osmotic pressure and the osmolarity of a 154 millimolar sodium chloride solution, this is not molar, this is millimolar solution. So you will just apply equation 1 and 2 for these. So equation 1 being used, pi is equals to RT phi IC. Just tabulate the values of each using the table and the gas constant, the multiple of this 22.4, using 0.93 from here and 2 from here, because this was sodium chloride solution. And since it was 154 millimolar, so 154 is divided by 1000, we get the answer of 6.42 atmosphere. So this is the osmolarity. We get the osmotic pressure here. Okay, so continuing here, so osmolarity can be calculated also as using the equation second, phi IC. So this is 0.93 into 2 multiplied by 154 upon 1000. So the answer comes out to be 0.86 osmoles per liter. So understanding how the principle of osmosis works, for example, 154 millimolar sodium chloride solution, which is isotonic to red blood cell. If you place this solution, your red blood cell in the solution, there will be movement of water molecules in both directions. The net movement of water molecule will be 0. So water moving in and out will be at a constant rate. So the red blood cells don't swell up, they don't shrink, so they stay of the normal size. This is how the red blood cells stay of their original size, and inside our blood vessels and the heart as well. But if the red blood cells are placed in a solution which is less than 154 millimolar solution, the red blood cells are placed in a hypotonic solution, the cell would start to swell and the cell will burst. So why the cell ends up bursting? Because water entered the cell. This was endosmosis occurring, water entering the cell. So when the water entered, the cell got swollen and it got burst. The reverse will happen if the red blood cells are placed in a solution which is greater than 154 millimolar solution. And when you place this here, hypertonic solution, so this crenation will occur and this will also cause hemolysis. The red blood cells lose water, spikes start to form on the red blood cell surface. This is why, because the osmosis is occurring, but the water is going out of the red blood cells, crenation form occurs, and you can, as I mentioned, the spikes can be seen as loss of water occurs, and red blood cells will start to burst as well. Your 0.9% sodium chloride solution or 0.5% glucose solution are also isotonic to the red blood cell. So that basically sums up the movement of molecules and how diffusion osmosis is governing transport of substances across the membrane. That's it from my side. Thank you so much.